Good afternoon, good morning, and to some of you, good evening. A warm welcome to our global audience. Thank you for being with us today as part of our three-part webinar series on PTP ST 2059. Today, of course, is our introduction info session, Keeping Time with PTP. This webinar series is presented in partnership with Telstream, Imagine Communications, and Arista. My name is Gina Angelia. I'm part of the marketing team here at Imagine Communications, and I'll be working behind the scenes today to help out moderate questions and take care of you, our audience. And as such, I do have a few small housekeeping items just to go over before we get started. Now, one technical note, please be advised if you are currently connected to a VPN service, know that it may impact the quality of today's broadcast. We do recommend that you disconnect from the VPN for the duration of the presentation if possible. If you're having audio trouble or are concerned about your audio connection quality in general, a reminder that a list of regional dial-in phone numbers was provided in your registration confirmation email. For those of you who may be new to the Zoom webinar platform, there are two key buttons I'd like to draw your attention to in this application. You should be able to move your mouse cursor to the bottom of the presentation window and find them there. The first is our chat window, where I will be posting any important information and messages should the need arise. And if you are having any difficulties in the chat window, you can contact me as well and I'll help you out there. The second is our questions submission button. We welcome everyone to add their questions to this box at any time during the live broadcast. All questions submitted, while they may not be answered live, will of course be collected and forwarded to our panelists. Speaking of our panelists today, we have three keynote speakers with us, as well as a few other experts behind the scenes ready to take on your questions. As part of the live broadcast today, you'll be hearing from Robert Welch, Principal Engineer from Arista, Lee Whitcomb, Architect at Imagine Communications, and our host for today is Mike Wadeson, Application Engineer from Telstream. To everyone on our panelist side of the call, thank you for being with us today. And with that, I'll hand it over to our presenter. Mike, the show is yours.
Thank you, Gina, and welcome everyone to this presentation on keeping time with PTP. I'm joined, as you say, by our host. With me as my host today are Robert Welch and Lee Whitcomb. And during the course of this webinar, we'll be using terms such as master and slave, since this is the language that's used in the standards today. Please note that when we use these terms, we're referring to electronic devices and not to people, and work is being carried out within the standards to change some of the terminology, and the standards will be updated in the future to reflect this information. So thanks for joining me, Robert and Lee, and welcome everyone to this presentation. Since the dawn of time, people have looked for ways to measure time, from early sundials or water clocks. Various methods have been used to quantify time. And over the course of time, the way in which we measure time has become more accurate, with the use of such devices as atomic clocks. For video applications, we have used analog reference signals which carry horizontal and vertical drive information with burst flag and some carrier embedded in our composite black burst reference signal. The signal is used to generate genlock, various devices within our video facility. Today, we not only use black burst, but we also have tri-level sync for HD signals and ensure audio synchronization with digital audio reference signals such as DARs. For network time, we've been using the network time protocol that provides a time reference for our computers and network devices to sub-millisecond accuracy across the network. However, for video, we need greater precision in the sub-microsecond level, and therefore we need to use precision time protocol defined by IEEE standard 1588. And during the course of this presentation, we'll take a closer look at the syntax and processes used for timing of an IP media network. In our traditional analog and digital reference systems, we'll have a sync pulse generator, such as the SPG 8000A, that provides a variety of analog black burst and tri-level sync reference signals, along with digital audio reference signals such as SDI signal generation, and then we'll have timecode in either LTC or VITC. For redundancy, two SPGs will be used as primary and backup generators that will be controlled by an emergency changeover unit, such as the ECO 8000, that will sense automatically a level change in one of the signals and switch from the primary to the backup SPG and provide redundancy within our reference system. Each of the various reference signals will be distributed by a DA across the facility and provide synchronization signals to a variety of devices within the broadcast network. Now let's take a look at how this would work in a PTP-based reference system. The SPG 8000A can be used to provide a PTP stream as well as the analog and digital reference. But instead of the ECO 8000 to be used for redundancy, the PTP syntax provides a method for redundancy using the best master clock algorithm. We'll discuss this later in more detail and the process in which determines which device will be generating the time. PTP will pass through the network either using a generic switch, but it's preferable to use a PTP aware switch that is capable of being either a transparent switch or a boundary switch. And we'll explain these terms later in the presentation. The media node receives the time signature via PTP and provides methods to synchronize the devices to the reference. An important part of synchronization within PTP is the use of GPS time. This reference provides accurate timing information. So let's spend a few minutes reviewing this system. Global positioning systems may be used for navigation, but they're also outstanding time references. The system works with 31 satellites orbiting the Earth, each with a precise atomic clock. Only a certain number of the satellites may be in view from one location on Earth at a time. The GPS receiver inside the SPG 8000 can obtain an accurate time of day by triangulating the signals from at least 4 satellites. Once we have a lock to GPS, then we can provide accurate time signatures, which can then be used to provide the time for our video references and PTP.
Mike, it's Lee here. GPS is it's a US-based system. Are there any other GPS-based systems that people can use?
Yes, Lee. There are several around the world being used today. In Russia, for instance, there's GLONASS. And in the SPG 8000A, we can actually use GPS and GLONASS together. That will increase the number of satellites that are available and enable us to position and fix more quickly and accurately on the time signature. But there are also systems in other parts of the world. So in China, there's the Beidou Navigational Satellite System, while in Europe, we have Galileo, in India, Navic IC, and in Japan, we have the Quasi-Zenith Satellite System, which is used in conjunction with GNS for Asia. So we've got a variety of those devices, and thanks, Lee, for the question. Remember yourselves, you can all ask questions in the chat, and we'll answer those at the end of this session. So please make sure to use that chat.
One more question though, because you mentioned the DA with the ECO on it, right? Or you got the SPG with the basically the blackburst coming in, and you've got the PTP coming out. It's one device, so you can feed both and keep both type of clocks the same from the one single device, right?
Yep. So both PTP and our references, and we're going to take a look at that next in this particular part of how it all works from the time point of view of when we get GPS. That provides us a very stable signal, which in its simplest terms produce a 10 megahertz continuous wave clock, along with a pulse per second and the time data. And that can be used by the SPG 8000 to generate time code, either in longitudinal time, LTC, or vertical interval time, VITC, along with our analog and digital reference signals. And that same time date information can be used by PTP for synchronization. But the question then becomes is how we convert timing information from GPS to our analog reference outputs as well. The 10 megahertz reference just isn't enough to align the video frames, and we need that 1 pulse per second and the time of day information from GPS to determine alignment of the reference signals. The SMPTE epoch is defined as January the 1st, 1970 at midnight, and is the big bang moment when all frames were aligned for analog and digital systems, and time as well. From this time, we've been counting how many seconds and how many nanoseconds have occurred from then until now. So if we know that value, we can count also how many NTSC frames or how many PAL frames have occurred since the SMPTE epoch. So for every 1,001 seconds, there are 30,000 NTSC frames and 25,025 PAL frames. From this information of the time now and the number of frames that have occurred, we can determine the point at which NTSC and PAL should be aligned at this moment in time for the video signals. In this way, we can ensure in synchronization of our video and audio signals within the system. Let's now start to take a look at the protocol itself, Precision Time Protocol, and we're going to delve into some of that syntax information and how the system works. In this presentation today, we'll be discussing the standard of IEEE 1588 for PTP version 2. This is the basis for a variety of PTP profiles. For the broadcast-specific applications, we have SMPTE ST 2059-2. That's the profile that's used specifically for timing of broadcast needs, such as daylight savings times, leap second, and drop frame synchronization. SMPTE 2059-1 provides us with generation and alignment of a variety of video and audio signals defined from the SMPTE epoch. For a variety of audio devices, we have the AES-67 standard, which has its own defined specific profile. In order to harmonize the differences between the SMPTE 2059 and the AES-67 standard, we have recommendations of AES R116 that provides for interoperability of video and audio across the IP media network. Now, these standards are continually evolving, and the IEEE 1588 has just updated the version of the standard to what's commonly referred to as version 2.1. Now it's backward compatible to version 2, and we'll primarily be talking about that today. Lee, perhaps you can tell us a little bit more about what's happening with some of the other standard committees.
Yeah, so there's actually lots of work going on right now with PTP related stuff. So in SMPTE, the 2059 standards, since they've been out in the field for about 5 years, are now going through a review process. And in the next couple of months, there'll be new versions of 2059-1 and -2 published. Nothing too radical, but just sort of some cleanups and clarity. There's also work going on. There's an RP being written on PTP monitoring. And what this is doing is defining standardized parameters and standardized encoding of those parameters such that all the different devices in the industry can sort of have a consistent way that monitoring devices can find out what's the status of PTP. There's also a study group looking at PTP security. And so it's publishing a report on sort of what are different threats that can occur in PTP, as well as some ways to mitigate that, so to help on the security side of PTP. And even though IEEE 1588 just released their 2.1 version, there were certain things that didn't make it in that standard. And so they've now started work on sort of updating that standard for sort of new features and new stuff. So there's lots of stuff going on the standards side in terms of improvements and enhancements to PTP.
You know, it's interesting, Haley, that you brought that up. Is one of the things I think that doesn't come to light is we have all these standards. There's basically text on paper, right? Follow these kind of rules. But we as an industry with the VSF and JTNM, and there's also Mike Overton lurking in the background answering questions. We're all working on actual interoperability and making sure that things scale and are tested. You want to talk to that just real quick?
Yeah, so there's been a variety of events where we've got basically various companies to come together to make sure, does everything interoperate together? There's the JTM tested program, which is sort of trying to make sure, do products sort of onto the standard. So there's various test plans. And at the last event we had, I can't remember, it was like over 50 or 60 companies and hundreds of pieces of equipment to sort of make sure, is everyone implementing the standard and the core parts of the standard correctly? So to help ensure that in the industry.
And the different topologies too. So we're considering different topologies, not one size never fits all. So there's a lot of interesting work going on, even so far as, hey, which interface do you get your PTP from, or should you get it from? So good stuff.
Yep.
Okay, great. So lots of work to be done, and we should catch up with the protocols here in the PTP and discuss that, and then we'll go through some of the various pieces. So let's, as I mentioned, talk about the SMPTE epoch. It's the big bang moment and the time at which all the signals started together on January the 1st at midnight, 1970. From this alignment point, we've calculated how many PAL, NTSC, AES, HD, and UHD frames or packets have occurred, and provide synchronization across a variety of different formats to a common time standard. So simply knowing the number of seconds and the number of nanoseconds from the SMPTE epoch till now, we can calculate how many frames or packets have occurred. And it's this simplicity of time that provides our synchronization across the network. The SMPTE 2059 standard provides us with the PTP profile for broadcast applications. In this next section, we'll discuss some of the key processes, such as the best master clock algorithm for determining which device is the source of time for the network, how the PTP messages are transported across the network, and the communication modes between devices. There's also specific broadcast requirements that are sent to devices using organizational extensions that contain the synchronization metadata. We should explain some of the terminology used for PTP. The Grandmaster clock is the ultimate source of time for clock synchronization across the IP media network. A master clock is a source of time for other devices within the network path that are synchronized together. A media node is a clock that may be synchronized to another clock. Within the network, we can set up various PTP domains for a logical grouping of clocks that synchronize to each other. For instance, we could have decided to have a video network in one domain and an audio network in another domain if we wanted to provide some separation for these logical groups. However, we want a single domain for our media network of both video and audio devices. So it's important to choose your domain or domains wisely for your logical grouping of devices to your Grandmaster clock. The domain value can range between 0 to 127, and you can choose a value of whatever you want it to be. Typically, that default value of SMPTE 2059-2 is 127. And for AES 67 and the IEEE 1588 standard, the default is 0. So we should ask what values should we use? And in some cases, why don't we recommend using the default values?
So this is that case where sometimes you go by the rule of thumb and sometimes you don't.
Yeah. So we'll cover a bit more like in my last presentation on commissioning. So it is kind of counterintuitive to say not use the default here. But you sort of have, one thing you have to keep in remember is that there's several parameters you have to configure in PTP. And if you don't configure these parameters correctly, it can kind of work, but not work correctly. And so you can kind of almost trick yourself into it's working when it's actually not performing as you expect. And so the question sort of comes down to, is it better to sort of partially work and be very confusing and be really hard to debug? Or is it better to sort of hard fail, it doesn't work at all, and that kind of reminds you, say, oh, I got to configure this device because I haven't configured it. Because then when you configure the PTP domain, you'll sort of remember, oh, I have to configure the sync interval and the announced timeout and all the different parameters. So that's kind of why we recommend here, don't choose the default. It's better to hard fail and then configure all the parameters correctly, then kind of soft working and not working correctly.
And the one main point here, and everybody's got to get this right, is it has to be on the same domain for everybody to lock that particular grandmaster or grandmaster pair. That's one point. The other point is you could have two different domains in the same organization, same facility, and you could do some onboarding to one domain, maybe the default domain, and then after you've got it onboarded, change it to the other domain if you wanted to. But just note that you're going to have multiple grandmasters, which I'm sure somebody would like to sell you more kit for. That's fine. You could do that too.
So just like Lee and Robert, remember that you can ask your own questions in the chat. So please take the advantage while we're all here together to ask your specific questions on PTP. We need to understand some of the syntax used within PTP and the different types of messages defined by the standard. Firstly, there's an announce message. This is used as part of the BMCA to provide the synchronization hierarchy and determine which device will become the grandmaster. Then there is the sync message that provides the time information in seconds and nanoseconds. In some cases, a follow-up message can be used to contain the time information rather than the sync message. Now that we have the time information, we need a method to determine the propagation delay between the grandmaster and the media nodes. And this is achieved by sending a delay request from the media node, and a delay response message is sent back from the grandmaster to the media node. So in this way, we can calculate, as you'll see in a moment, the time between the propagation from the master to the end device.
So how do you look at this on the wire, though?
On the wire?
Yeah.
Well,
can you use Wireshark or something like that?
We'll show you in just a moment some of those particular syntax values, so you can take a little bit of a look at where those values are contained and how they might look. And so we'll take a look at that in a moment. The other message I want to talk about also is the management message. It's used to provide the information to clocks. So for instance, in SMPTE 2059, the management message provides specific broadcast information on daylight savings time, leap second, and a drop frame. And so we can look at those particular pieces by looking at them in the syntax view. So here I captured some information from Wireshark, and then I've extracted some of that information for some of these specific messages. So the first one we're going to take a look at is the announce message. So we have an ID that identifies it as an announce message, and that's a value of B in hex. And this announce message is used as part of the best master clock algorithm, BMCA. It contains the domain value, in this case called the subdomain number, and our value is not 127 or 0, but it's 126. There is the clock ID, and this is the MAC address of the device. The first 3 hex bytes are the organizational unique identifier. So in this case, Tektronix has a value of 080011, and so that identifies the specific device or manufacturer that's sending out that information. You can see the timestamp that the message was sent out from the clock of the device in seconds and nanoseconds. The current UTC offset, this is the leap second value, which is currently 37, and the priority values of 1 and 2, along with clock class, clock accuracy, and clock variance, which we'll discuss as part of the BMCA later. So that's one particular message. Let's take a look at the others. So this is the sync message. Or in some cases, we'll use the follow-up message to provide the time information in seconds and nanoseconds generated by the master clock. You'll see that subdomain number again for the domain value that applies to the group of the devices, the clock ID, which is that MAC address of the sender. And here, in this particular case, you can see the very similar syntax value for the follow-up message containing that time in seconds and nanoseconds. The media node sends a delay request message to assist in measuring the propagation delay from the media node to the master, while the delay response message provides a timestamp from the master to the media node once the delay request message is received by the master. You again can see the subdomain number, that's our domain value, the clock ID, the MAC address of the device, and the timestamp information in seconds and nanoseconds from the device. Here's the value for that delay request. It's very similar. And you can see here, there's the MAC address of the sender. And so we've got these two specific values that we're going to talk about a little bit later on how we measure that offset in time and the propagation and delay across the network. The other message that we're talking about today is the management message. This provides unique information in the case of SMPTE 2059-2 profile with the time length value, TLV, for the SMPTE metadata. It provides specific information for broadcast applications. So here you can see the specific SMPTE 2059 data with the current local offset for UTC, that is currently the leap second value of 37 seconds, the time in seconds of the next jump when specific values will be applied for such things as daylight savings time or drop frame sequence. Each of these messages that we've discussed so far has a rate at which those messages will be sent. This can be sent by the profile used or set by the user for specific requirements. For instance, announce messages can be sent every second, and sync messages may be sent every 8 times a second. The rate at which these messages are sent can be an important characteristic to monitoring of the signal and making sure your system is working reliably. Now let's take a look at the best master clock algorithm and how this works to choose the grandmaster clock within the system. In our typical redundant system, we'll have 2 SPGs locked to GPS. And if one of these devices loses lock or is disconnected from the system, then the BMCA will determine which device should be the grandmaster using syntax within the announce message. Here is an example of our system with 2 SPGs that are locked to GPS, and we have a variety of media nodes on the system taking part in PTP. Initially, when all devices are powered on, PTP devices listen to the announce messages to determine which device should be the grandmaster. The grandmaster is determined by the values set in the announce message, and there are several rounds in the BMCA competition to determine which device will be selected. So the BMCA runs on all devices, and it's based on these several parameters, starting with using user-defined value for priority 1. This has a range from 0 to 255, and the lowest value within the range of devices wins the competition. So typically in the SPG 8000A, we have a default value of 128. Device with the lowest value within this BMCA competition will win. If there's a tie, then we go to the next round, and this is based on the clock class, the clock accuracy, and the clock variance, set by devices themselves. So depending on how well they are locked, for instance, if a device is locked to GPS, it'll have a clock class of 6, where other devices not locked to GPS will have a higher value. Then, if everything is tied again, we'll go to a third round. And this is again based on another user set value for priority 2, with a range of 0 to 255, and the device with the lowest value will win this round. There is one final tiebreaker, and that is based on the clock ID, which is the MAC address of the device. And since you have a wide variety of values for this that are chosen by the manufacturer, and you have no control over what this value actually is for your system, you need to make sure that you choose correct values for priority 1 and priority 2 to make wise decisions on choosing which device will be the grandmaster.
Could you go back just one slide, I think, real quick? Gina, there was a couple of questions posed that were over and over again. You want to kind of let us know what those were?
Yeah, we have a couple of interesting questions that have come in, and just as a quick reminder, since I've been given the floor back, please make sure that you're using the Q&A box to add your questions so we make sure that they are seen and collected, and we'll go through a number of them at the end of the presentation. But right now, are you able to give a practical example of when the default values are not recommended?
That would be pretty much the domain. The domain is the main thing. The other things are, and I had this situation last night. Somebody had the sync interval configured wrong on the switch. And so if you've got it configured wrong on one side and the other side, or they're, kind of mismatched, you're not going to get lock. So it's best to have them consistent across both sides and also on every link. And we didn't get into that. We'll show that in the next architectural discussion about best practices. But for the most part, the one thing that you can have a variance on is just the domain itself. And then we're going to get into this a little bit more, P1 and P2. But those things that you can't really have control of are class, accuracy, and variance. Those things are more derivable than anything else. But so you'll see the P1, P2, and the domain are the threes that you have control over, I'd say. Lee, do you have any other comments?
Yeah, and I think Mike maybe covered this in a few slides, so maybe just jumping ahead. When it comes to the other parameters, things like sync intervals and announce interval and stuff, they're very, for the most part, you should always use the defaults. Lots of thought has gone into choosing those defaults, trying to choose a nice performance point between lock time and stability and everything. And those have been tested in many, many field deployments and at all the various interop events and JTM test events. So unless you have a really, really, really good reason, all the other parameters you really should use at the defaults. There's very few excuses why you shouldn't.
Yeah, I had one guy debate with me. He goes, I'm just going to use 1588 everywhere. And I'm like, dude, it's not tight enough. You got to have a specific, this is why we spent almost, what, a year and a half on the original 2059s to say what those values should be.
Yeah, there's a lot of
sorry,
values.
Back to you, Mike.
Thank you.
Yeah.
There's a lot of values, and with the ability and flexibility you have, there's a potential that you can set the wrong value somewhere in the chain, and that can throw off the system. So it's very important to choose the right values and then make sure that they're consistent across the whole of the network. But values that you don't get to set are the values for clock accuracy, clock class, clock variance. Those are actually defined by the device itself. So there are a wide variety of these values in the standard. We'll focus just on a few of them here. As we've mentioned already, GPS has a clock class of 6. And if a device is locked to GPS or was locked to GPS, but is no longer locked to GPS, it may be in holdover mode. And then it'd have a clock class of 7. In other cases, if you look at a device that's internally locked, it's not locked to GPS, then it might have a value of somewhere in the range of 248. And then it might be termed handset. So it's internally locked, but it's not locked to GPS in this particular case. Clock accuracy defines the range of how accurate the clock is within a device. And typically those are determined by the manufacturer of the device on how accurate the device is when it's locked, for instance, to GPS. And it'll likely select from an allowed set of values that are within the standard. It doesn't necessarily mean that the device has calculated these values in real time. It's just said, if I'm locked to GPS, this is time accurate to within this range. So those are values which the device actually gets some control over, determining automatically for you, while other values are values that you can specifically define. So we mentioned the announce message contains the values in the BMCA, and you can see where those values are for priority 1, which is a value you get to set as a user, the clock priority, which is set by the device, and the priority 2 syntax, which is also user defined. Notice the domain value is referenced along with the clock ID and the time source. In this case, it's handset. So that means it has a clock class of 248, meaning this device is likely internally locked at the moment. Now let's put this all into practice, what we've learned so far, and perhaps Lee and Robert can guide you through the process of which device is going to be the grandmaster.
I think he's going to trick us, Lee. So
Yeah. Okay. So let's do this carefully. So the
Okay.
first, the top level is priority 1. So if I look at the one on the left, its priority 1 is 1, and the one on the right, and the one on the right, its priority 1 is 1. So they're tied. So I guess we go to the next tiebreaker.
Yep, because it goes P1. Well, hang on a second. So let me get this right. P1, then all that variant stuff, and then you got P2, right? And then in that order, right?
Yep. So I guess if we look at them, so both of them look like they're locked to GPS. So I guess
Oh,
both of them have.
one more thing, Lee. Sorry, didn't mean to interrupt. The ones priority 1 down below are 10, and then lower the number, basically the better the number, right? So 1
That's
is
right.
definitely lower. At least, yep, 1 is lower than 10. I just checked.
That's right. Yeah. So one's lower than 10. So we're really only looking at the top two devices. And let's see, both of the devices are locked to GPS, it looks like. So I guess the clock class is the same. And I guess we'll assume.
Speaking of which, Lee,
Yep.
Mike, sorry, I keep interrupting. I feel like Columbo. I just got one more question. When it says it's locked, is it 3 birds, or how many birds are we really locking to?
So we need at least 4 satellites to be locked together.
Okay,
GPS.
so if you just happen to be at that precipice, it's going to be not clock class says, it'll go to what, like a 7?
So yeah, if it'll go to, so if there was something that GPS was lost for a moment due to atmospheric conditions, for instance, then we go to a clock class of 7, saying we were locked to GPS, but now we're in holdover mode.
Okay, so we're going to say we're at 6.
Yeah,
Yep.
but we're at 6 in this example.
Yeah. Okay. So it looks like all the top things are all tied. So then I think the next one is priority 2. So I see the one on the left is 10, and that's a lower value than the one on the right, which is 11. So the priority 2 will go to the one on the left. He'll win. So I'm gonna say the one on the left is the Grandmaster.
Final answer.
Final answer.
Okay, and you're both correct. Well done. Thanks for playing the BMCA game. But we're not over yet because we got another round to this competition. So let's take a look at another example.
Please don't be sports trivia. Oh, okay, go ahead.
Okay. Let's imagine that GPS has been lost due to atmospheric conditions. So the primary master may have been hit by a lightning strike on the antenna, and there's no GPS from that device anymore. So it's going to go to a clock class of 7, as we've mentioned. But what's going to happen now?
Okay. So
1 and 1.
So 1 and 1. So we're still tied on priority. Okay. So the next thing is we look at clock class. So the one on the left, you said it moved to 7. And the one on the right, it's going to stay at 6.
Right.
And since 6 is less than 7, it's going to win the BMCA. So I'm going to say it's the one on the right is now going to become the Grandmaster.
Yeah, because it goes P1 and then all that accuracy stuff that we were talking about, then the P2. So it's in that order. So I agree. Lee, final answer?
Final answer.
So you're both correct again. Thanks for playing this round. So yes, so because the clock class is being used in these cases, so because there was a tie in the priority 1 value across all the devices that were taking part in this particular process, then clock class and clock accuracy were actually used to determine which device would become the Grandmaster. And that's what happened in this particular case. I've got one more example that we could do. Yeah, now I've changed the priority 1 setting for one of the devices, and that's all I've done.
I see.
So what's going to happen now?
The upper right one, you changed to 10. I was flipping it back and forth in my head. So yes, the 10 is definitely higher than 1, right?
Yeah.
So
I guess.
I think.
Go ahead.
What do you think? I was going to say, as we got P1. P1 is always the first tiebreaker. So if nobody else is P1.
Yeah.
So I see.
I'm going to say upper left too, but this is kind of weird because the one on the upper left, it has no GPS feed, so it's in free run. So even though the one on the right is actually providing better time, the one on the left is actually going to be the Grandmaster. So this is kind of looks like a poor choice of settings. But I'm going to vote.
As long as it's domain, and we're talking about, all these are on the same domain too. So yes, so that means that he's going to win. So that basically, Mike, what you're saying is priority 1 is like king or queen or the ultimate Uber thingy, right?
Yeah,
so you got to make sure you get your P1 right, consistent, right, and then play around with your P2. I guess that's what the whole point of this is.
Right. So the situation is, if I was doing things like I did in the old days for my analog reference signals, I would have put my GPS device in the top of the rack, and that would be my primary. And then the one below that would be the secondary backup system. So the rack location might have determined which device was the primary and which device was the backup. And that was my kind of control of my choice of primary and backup. So within
Okay.
PTP, I can decide to do that same thing if I choose my priority 1 value to be low for one device and all the others to be higher than that. So in this case, I didn't care about clock class, I didn't care about clock accuracy or variance. All of those particular pieces don't matter because I've decided I want control over which device is going to be the grandmaster, and therefore it's always going to be my primary device. If I
Yeah,
want to,
I was
if I
gonna say
want
in
to,
this particular case, he's
go
not
ahead.
doing BMCA. The one the upper left is not doing BMCA with anything. He's just sitting there,
Right.
kind of, right? But
So
the other three, well, actually, yeah, I guess they are all doing BMCA. They're all in the same domain,
right.
and they're just this one's just going to win all the time.
Yeah. Now, if the connection got broken for some reason, somebody disconnected both of the two upper SPGs. So if this cable and this cable were disconnected, then we'd have an ability in PTP to go to the next level. So we could choose the next level and we'd go down and we'd look at our other devices and we can see priority 1 for these two devices is 10. So they're both equal at that particular level. Let's assume that clock class, clock accuracy, and clock variance are also equal for both devices. And then we're going to choose the priority 2. So in this case, because this value is 20 and this is 21, then this one would become the grandmaster if the others had somehow failed or been disconnected from the system. So you can provide multiple layers of redundancy. You don't just have to have a primary and backup. You can have a third level. You can have a fourth level within the system.
So basically you're saying now with IP-based 1588, 2059 systems, we have a lot more flexibility and power than we did back in the old sort of analog ACO changeover days.
Exactly. And that's why it's so important to set your priority 1 and priority 2 values for your system correctly. But you need to make sure that they're appropriate for what you expect to happen. So like in this particular case, we've set them to a good particular process, except I want to now go back and put that SPG up here back to a 1 instead of a 10. And then we'll be back to a good redundant system within our case here.
Okay, very good.
Okay, thanks for playing the BMCA game. Now we've determined primary master using the announce message. Let's look at some of the other messages that are sent through the network. So the master will send out time information in the sync message at T1, and it will then traverse the network and be received at the media node at T2. The media node will periodically send out delay request messages at T3 to the master, and once this message is received by the master should send out a delay response message at T4. So for these values from T1 through T4, we can calculate the time from the master to the media node and the time from the media node to the master. And using some very simple maths, we can calculate the offset value, the time difference between the master and the media node, and we can calculate the propagation one-way delay of the system, assuming that it's symmetrical, right? So that we have to assume that the time it's taken for the path to go one direction is going to be the same path that we go back in the reverse direction. And these calculations are done by the devices based on the rate of messages sent between devices. So it's a continual process of making this calculation. So remember that message rates typically are 8 messages per second in SMPTE 2059-2. So these are messages are 1/8 of a second between each of these values that are sent. Within Prism, we can plot the master to slave and the slave to master delay graphs for the forward and reverse paths and watch the variation in performance of the network in real time. Ideally, the two paths should have similar plots like in this case. So the graph should look fairly flat and nice and straight lines across the display. There'll be some variations as that toing and froing happens across the network. But once they converge, they should look very similar graphs between the forward and reverse paths. We've mentioned that the message rates can be set by the user and the devices, so it's important that you ensure the device is receiving the messages at the correct rate. Here in the Prism session display, we can look at the sum of that PTP metrics that the media node is receiving. Firstly, we can check the domain value, that it's appropriate for our network. We can see that priority 1, the clock priority, and priority 2 values used, and we can make sure the master is locked to GPS. We can also see the message rates for SMPTE 2059 profile. So there's 4 announced messages and 8 sync, delay request, and delay response. So we can see those and we can make sure those rates are happening correctly between devices. If we were looking, let's say, at AES 67 profile, then we can see that it has different message rates. So the announced message is sent once every 2 seconds, and the sync, delay request, and delay response messages are sent every second. We could have also some generic profile that we've defined ourselves. We've set the message rates for our particular system, and so that would have kind of a generic more profile of what you've decided to set as the message rates. In the IP media network, typically we'll use both video and audio sources, so we want to harmonize the interoperability of the SMPTE 2059-2 profile and the AES 67 profile. This is done in AES R16 report and provides recommendations for the values to be used for the IP media network. So you'll see recommended values for domain, announce interval, and sync interval. But hang on a minute. We've got negative values. How can we have negative values of time? What's going on here?
Oh, we're going backwards in time, Back to the Future. No,
Yeah.
it's basically it makes it reciprocal of. So it just basically take the way I think of it, take the numerator and make it a denominator. So it's a fraction now. By the way, we only have about 10 minutes to go, so just heads up.
Yeah,
Okay.
it's also for the numbers there, it's actually 2 to the power of that number. So in say the case of log sync interval, it's 2 to the power of -3, which is 1/8, and since that's the interval is 1/8 of a second or 8 messages a second. If it was the value, say -4, it would be 2 to the power of -4 or 60 or 1/16 or 16 messages a second. So you just have to remember that those numbers in the standard are 2 to the power of n. And as I sort of mentioned before, it's highly recommended that you keep with the recommended values. So the announce interval of 1 message per second, the sync interval of 8 messages per second. These have been sort of the pros and cons of changing those have been debated highly in the standards committee. We've tested those in all the various interop events, and they're highly deployed in the industry. So we know those values work well. So other than the domain interval, which is sort of up for you to choose, those other values, you really, really should keep to the defaults. It's in your best interest to keep with those.
So Mike, can you show us some examples of some of the topologies?
Sure. So we're going to go through and look at firstly look at the PTP clock types. So just to understand that there is within these different types of clock, there's obviously an ordinary clock, and that's a media node. But we've also got the ability to have transparent clocks. This is a switch or a router that accounts for the delay in processing of messages from arrival to departure and adds that difference in time as a correction field in the message header. A boundary clock is a switch or router that receives the time from a master on one port and provides multiple master ports to downstream media nodes in the domain, and provides a boundary between the grandmaster and the media node. Let's take a look at that. Here we can see an example of how this would work in a network, with the grandmaster sending message to a transparent clock, which adds a correction factor to the outgoing message to account for queuing of the messages through the switch. The media node then can take account of this delay in the calculation of time. In the other cases, the use of a boundary clock creates a boundary between the media node and the grandmaster, meaning that the number of devices the grandmaster has to communicate is smaller, reducing the load on the grandmaster, meaning it just doesn't have to work too hard. Remember that the message rates are relatively low, at once per second or 8 times per second. Typically, however, when we multiply this by the number of devices in the network, then the load on the system can cause problems in the network, especially when you've got these large data rate traffic for video and audio media across the network. So you want to structure the loading appropriately across the devices within your network. And that brings us nicely to communication modes of how we generally send messages between devices. We're going to cover 3 types here, starting with unicast, which is a one-to-one communication. This is like having a conversation between 2 people. However, in a network, we want to send information to multiple devices, and we could broadcast it to all devices in the network, but that would increase the loading on devices who don't want to receive that information. So typically we use multicast, where devices subscribe to receiving that information. Just like all of you today who decided to join this webinar to receive this information about PTP. However, in some cases, we may want to stream these messages between devices, and therefore we can use the SMPTE mixed mode to negotiate that some of the traffic will be sent as multicast and some of the traffic will be sent as unicast. Let's take a quick look at that modes of communication. Here we can see unicast communication. This is a mode that's going to communicate between one device to another. So let's say the grandmaster is going to send out a message, and that's going to go to a media node. It's a one-to-one communication. In multicast, we're sending PTP messages using a multicast address of 224.0.1.129. And devices wanting to receive PTP messages subscribe to this multicast address. This means that messages such as announce, sync, follow-up, delay request, delay response, and management messages are sent by this mechanism. So we've got this particular mode. So we're going to send a message out from the grandmaster, and the switch is going to replicate that message and send it out to all those devices who've subscribed to that message. So those are our unicast and our multicast ways of sending the information. Now, there is a way to improve those particular messages, and we can send multicast messages on that address of 224.0.1.129, and then all the devices will be receiving that and subscribe to that multicast address. Or we can use this SMPTE mix mode, which allows us to separate certain of the messages as multicast and certain of the messages as unicast. So devices want to be able to be sending out announce, sync, follow-up, management. They should all go as multicast addresses. And then delay request is sent by one device, so it could just communicate in unicast to the master. And so they can also send that delay response over the network in unicast because it only needed a one-to-one communication for those specific messages rather than sending it to every single device within the network. So multicast would broadcast it to all those subscribers, so even other media nodes would receive those messages and they would just throw them away. Another way to prioritize traffic is use the differentiated services protocol to ensure that the PTP messages are processed as quickly as possible. And this minimizes the delay of processing in the switching devices the PTP packets. So they get priority in moving through the network. So we want to send our PTP messages to expedite their forwarding with a value of 46, so that switches will then put that and make that traffic jump the queue more than other particular pieces in the network. Now let's put it all together. Here's a basic topology in the network in this presentation. We've discussed it kind of already. We've got a primary and a backup system configured appropriately with priority 1 and priority 2 messages. We're going to use a transparent switch to account for processing delays through the switch and to limit messages to the grandmaster, we're going to use a boundary clock. So that means that the media nodes will be talking to the boundary switch, but they don't have to then talk to the grandmaster device. So effectively, our boundary switch is acting like a PTP DA within our network topology. Now, this is just for a single network device. Suppose we have a primary and secondary blue networks. Well, here we could put our SPGs on either side of those networks, and they would then provide PTP to the primary network from the primary master, and the backup master would provide it for the secondary network. But really, we want to have some redundancy within those PTP masters. So let's add a link between the devices. So PTP messages flow between those two switches only. And so the primary master will now take over the negotiation in the BMCA. So the primary master, if it's set right for the priority 1 value, will become the grandmaster and the time of reference for all of the system, both the primary and secondary networks in this particular case. And therefore, the backup master will go to a passive mode. So it'll be waiting in the wings to take over if necessary, but it'll be passive and not sending out the announce message, which will be sent out by the primary master. So this will be sending out the announce message, and the backup master will be in a passive mode. Finally, another kind of topology that we would look at is having multiple locations. So you might not just have a single facility, but you may need to consider it across multiple locations. And in this case, we'd recommend having its own primary and backup master for each facility locked to GPS. Then they'll have a synchronous time source between the two sites. And if you were using PTP across the wider network, so you sent it across the cloud, it's possible that there could be problems with longer delays introduced across that network path. So that's why we're typically recommending that each device, for its redundancy and for its network reliability, have 2 particular GPS SPG systems in that network. So that brings us to the end of the presentation part. I hope that we've got time for a few more questions, if people are willing to stay on the line for a little bit longer.
Yeah, Gina, there was a question, but why don't you come on? And by the way, a lot of the details that were in the last couple of slides, that was just the tip of the iceberg. It was a trailer, a teaser, if you will, for the next one, which will go into architectures and best practices and detail this in great detail. Gina, how you doing?
Great. I really enjoyed the session. Mike, thank you very much for your presentation. Lots of great detail. It's an introduction to me for PTP. I really enjoyed it as well. So yeah, we've had some really fantastic questions coming in from our audience. Thank you. We really appreciate that. Our panel has been working furiously behind the scenes to respond to as many as possible. And yet we're technically over time, but again, appreciate those that can stay with us. I'm going to ask the panel one more interesting question that came in, and it kind of goes like this. Could you have PTP version 1 and PTP version 2 signals passing over the same PTP hardware? And what is the switch? What's the boundary on the clock?
Okay, so let's take this back just a bit. If you go back a couple of slides to one where you have the grandmasters and the media node connected to it, Mike. The answer is yes, you can do this. And we'll typically see this in like Dante Ravenna type environments where they say you dictate, PTP v1, and you typically plug and play that stuff. Now, by the way, Dante has progressed forward. You can configure with the Dante Domain Manager, DDM as we call it, PTP v2 on all the systems, okay? So you can move towards PTP v2. But the question was, can I do both? Okay, so if you'd see that media node, if that media node is connected to an Ethernet switch, and that one media node is going to be PTP v2, then configure that port as a boundary, okay? Meaning that it's going to be a PTP role master, and you configure it for just that. The other ones, just configure it with no PTP profile at all. Just let it do multicast, just like you do today in a Dante environment, Dante switch. You plug stuff in, you're not configuring PTP, and it just all works. Or AS67, where first one in becomes a PTP grandmaster. So you just let the multicast happen for PTP v1, And those that you want to have the more 2110, 2059.2 stuff, configure those for PTP. So configure PTP for the SMPTE stuff and configure no PTP for all the PTP v1. Was that fast enough?
The only thing I'd also added is to minimize system complexity, as much as you can move to having a single standard like V2 in your network, it'll simplify things. So while you can do it, as Robert said, I would try to move towards upgrading everything to the V2, and that way you just have a much simpler system, which is then easier to maintain and operate and debug.
Excellent. Thank you, Robert, for that, and Lee as well for jumping in there. So now, yeah, we do have several other questions that unfortunately we've run out of time for, but I think a lot of those topics will be covered in our next 2 upcoming webinar sessions. If we just want to put up that last bit of information for everybody still on the line. Perfect. Thank you very much. So yes, of course, we have 2 other sessions coming up in our PTP series over the next 2 weeks. We're going to talk more about architecture and best practices, and then follow up with commissioning and troubleshooting. So today was a great introductory session, and hopefully a lot of the questions, like I said, we were able to answer a number of them, and you'll get even more details and in-depth coming up with the next couple of sessions. So on behalf of Mike, Lee, Robert, and everyone behind the scenes, thank you for our audience for being with us today. If you'd like any additional information about our presenters, the companies, or our product lines, we invite you to visit us at arista.com, imaginecommunications.com, and telstream.net. So once again, thank you with that. We certainly look forward to everyone joining us live in our audience again for the next 2 sessions. But right now, I'm going to close it out for today's webinar by saying thank you again, and we hope you have a great day. Take care.